Hello. I've been interested in learning game development for the past year or so. And when you start learning game development, you are exposed to modern programming engines, game development engines, such as the Unreal Engine, Unity, and Godot, all of which impose upon you an object oriented, inheritance based paradigm, where your entire game is composed of game objects that inherit features from each other. Now, I decided to start building a game from scratch. And the game I'm currently working on is text based, so it's entirely logic and data structures and has no rendering. This allows me to use whatever programming language and whatever programming style I want. And because I was also learning Rust, which is a low level, memory safe programming language that happens to take advantage of key features such as enums, pattern matching, and extreme type safety, I thought this was a great time to learn a different data structure than the typical object-oriented data structures that we see in gaming. This allows you to massively optimize usage of memory in games, and I'm going to show you why. So the first thing we're going to look at is the current norm. On the right hand, you see a scene view from the game engine Godot's editor. And it is heavily object-oriented. We are, in this example, creating a player object. And it's using inheritance. So each node under that player in the scene tree is actually inheriting functionality from the one above it. So idle, air, and run, which are part of the state machine, inherit functionality from move, which inherits functionality from state machine, which inherits functionality from player. Game objects are also heavily abstracted. You really don't know what's going on under the scene unless you program some of these components yourself, such as the collision shape 3D has tons of built-in functionality from Godot that you would have to kind of peel back the hood in order to see what's actually going on there. And this is not very beginner friendly. It isn't in the case that it gets you up and running into a full 3D game fast. It isn't in that you don't understand the computer science of how your game works. So the Rust programming language, if we were to create an object-oriented game object in Rust, we have this example here of a goblin, and this is the most naive approach I could think of, which is you basically just stuff all of its data into fields in a struct. So we have its UID, that is a unique identifier that allows you to interact with it directly. We have its name, we have its health, a Boolean to determine whether it's alive or dead, which you may use for various game systems. And then we have 3 dimensions of position and then 1 dimension of rotation. Again, this is just an example. This isn't how you might actually structure a game object. But the data in this example is not separated. It's all stored together contiguously behind this struct in memory. And then when you want to create it, you have to use factories, which are very common. And these Boolean flags, every time you have an if, else, or then statement, it creates a branch in the assembly. And so when you are executing code, it will make a prediction as to what branch is most likely to be taken. And you can even have some influence over which branch it is most likely to guess using the unlikely and likely keywords in Rust. But at the end of the day, it is still a prediction, and it can be wrong. And branch predictions can help slow down the control flow of your program. So it's not ideal. And these structs, in typical object-oriented fashion, have their own functionality. So on the top picture, you see that we are implementing Goblin and giving it a function called transform. And this transform takes itself and mutates it to the new values that we're giving it. So we're adding X, Y, Z, and rotation to the current values in order to move and rotate the goblin. And then in the main function, you can actually see how we would use what we've written here so far. So we would create the goblin factory, and then we would use the goblin factory to spawn one that we named shrimp for no reason. and then we apply a transform to it. Now, this becomes problematic in the cache line. So on a modern processor, there is 64 bytes of what we call the cache line between the processor and its cache and its memory. And this is what fills up basically on the way to the CPU in order to be executed. This is the first place the CPU will look in order to execute on data, in order to fetch data. And so it's important that you have as much relevant data. You want as much important data to be in that cache line at the right time in order to have maximum performance. One of the reasons that this is true is because in modern computing, memory sizes is ever increasing. My computer, for example, has 64 gigabytes of memory, which is you would have been unheard of a decade or two ago. And it's not, there are professional computers that have 256, 512 gigabytes. We're going to be seeing terabytes of RAM in the near future. So that is not a realistic bottleneck. CPU speed, however, is a real bottleneck. We are kind of reaching this area where CPUs aren't getting any faster. But even though that is the case, that is not the most common bottleneck in modern computing, actually. The most common bottleneck, and the reason why some software runs just as slow on a fast processor as it does on a mediocre processor, is because the cache line is being used extremely inefficiently. So let's say we're operating on some goblins, and then we want to operate on something completely different, like a dragon, and it has a different set of structs. It's stored in different place in memory. If it takes up more than 60, if it takes up too many bytes in memory, we will have to flush the entire cache line and reload it with new information. So when you do that, let's say you're pulling in 4 bytes of data, for example, the next 60 bytes will be whatever is next in the cache line, not necessarily whatever is the most relevant to your program. Because of that, we need to plan ahead so that the next bytes after what we are accessing are what we are most likely to actually access next. So this is a rough example of what our previous Goblin struct looks like in memory. Each struct is roughly 256 bits, and we have all the data just lumped together. So if we just wanted to check the name of a goblin, and let's say all the goblins are stored together in a vector, we would pull in that entire vector, which would completely fill the cache line, and then we would go to just the one and find its name. So you can see how that's extremely cache inefficient. So there's a couple enhancements we can make to this object-oriented approach right away without completely shifting our paradigm that make the cache line use much more efficient. And the first one is one you may have heard of before, and that's separating hot and cold data. So hot data is things that you're going to be executing constantly, maybe even every millisecond. This is updating position, updating lighting, updating things in the physics engine. These are things that happen constantly over and over and over, and that's hot data. And then we have what we call cold data, things that are maybe accessed on command by the user or every once in a while, elements that get sent to the UI, names, stuff like that. We can separate these into 2 different structs and then kind of link them together. And this allows us to have a cache line full of hot data when it's needed for fast computation. Another thing that we're going to do is extract behavior. So instead of the Goblin object itself having methods, so we would call transform on each goblin independently, we call transform on all the goblins, and then it'll operate over all of the hot data that's available. The last thing we can do, which doesn't have to do with the cache line, but is very easy in Rust, is to get rid of Boolean flags and instead use enums and pattern matching, which instead of creating branching instructions, it uses a lookup table to determine what to go to next in the assembly. This is much faster as there's no prediction involved. So here is an example of how we are transforming just the hot data. At the top, it's a function called transform. It takes in all the relevant hot data and applies transforms to it. And then we have that same main function earlier, but adapted to this new method. So we are transforming just the hot data of shrimp, our goblin from earlier. But everything else is the same. And again, this is just an example. I want you to imagine that there's thousands of these goblins held in a vector, because that's how game worlds are actually composed typically. And this has better cache line usage. So as you can see, we have twice as many goblins that we can operate on in the same amount of cache. So before it was 512 bits, 256 for each struct. Now we have only 128 bits for each struct. And so we have twice as many available in our cache line, which reduces the amount of misses. It means that evictions happen less often and we are fetching what we need more often. And then we can also store the cold data in something like a hash map, which allows us to have basically instant access to it through a lookup. And we can kind of separate the way we think about hot data and cold data, which leads to writing better software. Now this still has a scaling issue. So as our game grows, let's say we have 1 million objects, which is possible in certain kinds of games. And let's say that these objects, even if there's less of them, could be complex. They could have hundreds of fields. They could have all kinds of different functionality depending on what the game is doing. If there's animations and sprites and visual components, all of that adds to the game struct. And so then you start having to separate not just hot and cold data, but different systems from each other. And so we are either, in order to kind of maintain code like this, as we add more and more features, we're either forced to use inheritance, where let's say anything that has a 2D sprite has some of the same functionality. And so we inherit from something, maybe we call it a 2D object, like we saw in that Godot example earlier. Or we have to reinvent the wheel every time. And for every single feature we add, every single component we add, we have to write more code to do the same thing that we've already been doing. So this has a huge scaling issue. And so there is a solution to this, and it's something that's been out for a very long time. The first examples of it being used in gaming was, I believe, in the 90s, maybe even earlier. But it's re-emerging as we've discovered that memory usage is often a bottleneck. And this is the entity component system. And there's essentially 3 aspects to that. There's entities, which are just a U32, basically an ID to link things together. There are components. A name is a component, a position is a component, a health is a component, a sprite is a component, but they're separate. They're not stored in a struct with the entity. They're self-contained, and the entity is just linked to them. And then there's systems. Systems are functions that operate over components of the same type. So, for example, a system that only updates the sprite will take all of the sprites and update them according to how they're supposed to update, and will have no knowledge of the rest of the struct. So this is an entity component system. And here's an example of how we would do something like that in Rust. We still need a struct to hold state, and that will be our world struct, as you can see here on the left. This has a pool of entities, which is just our U32s. We have our names, which is a hash map that links the ID to the string, which is the name. Same thing with the HP pool. I made HP a struct in this example. That's why it has its own identifier. And then our positions are just vectors, because this is hot data, and so we want it vectorized of floats. And on the right here, we can see how you initialize one of these entities, because it's not as simple as just instantiating a struct. We have to, once we have created the world, this is a function within world. It's an implementation of world where we assign an ID to this new number, let's say it's 5, and then we insert into hash maps all of the relevant data, such as the name, HP, and the status. This is cold data. And then we push onto the vector, the world's vector, all of these, the entity's positions. And for this to actually function, you do have to create a somewhat more advanced data structure called a sparse set, which I will talk about later. But this is a simple way to look at the ECS way. And here's an example of a system. So we have a system that we call X transform. Notice it's not just transform. We're not just moving all the x's, y's, z's, and rotations together. We're doing one at a time, where it iterates over every single value in the position x pool and applies the transform to it. And again, this isn't how you would do it in an actual game, but it's an example. So here we have shrimp, who is spawned into the world, and then we apply the x transform and we move shrimp forward by 1. So if we had a vector of 1,000 goblins, they would each have their own place in the vector of x positions, and we would go over all of them and move them all forward by 1. So it's not actually an example of how a game would work, but it's how you might iterate over these vectors full of components and adjust them. And here's an example of what the cache line would look like if you were to do this. We have 16 goblins now in our cache, not 2, not 4, 16, in the same 512 bits that we had earlier. So you can see how if your game had hundreds of thousands of entities, how you would get significantly better cache performance out of storing your data this way. And so the next thing I'm going to do is walk through some example code for how we would do such a thing. All right, so this was our first example, the naive object-oriented one. So you can see how I laid out the structs here, and then I created a implementation on that goblin and a function to transform it. And then we have our factory here that creates these goblins with a unique entity ID that allows us to access it directly, and our code here to execute it. This was our next implementation, which is the slightly better object-oriented approach, where we separated the hot and cold data. And here you can see it's using the exact same kind of goblin factory, except the goblin has 2 smaller structs within it, the hot data and the cold data. And we also are using an enum for the alive status to reduce branching. And overall, the API is the same. You would almost use this exactly the same as how you would normally, but it's just significantly faster and has better cache performance. And it also allows you to store cold data in hash maps if you chose to, which is better for accessing. And then finally, we have our ECS approach. And this one is going to look a little bit different, but it has the same functionality essentially, where we have this world and we create these pools to hold all of the data in our world. And then we initialize the world itself, just like we were initializing the goblin earlier, except when we want to create a goblin, it follows something different. Instead of creating a struct, we are just creating an ID, which is what gets returned by this function. And then we are inserting into hash maps the relevant information and pushing onto vectors the relevant information. And so I have written out an entire game basically using this, except the game that I'm currently writing doesn't require any performance. Everything is held in hash maps for basically lookup tables, because there isn't a large entity requirement. The only reason I'm doing it the ECS way is because this has been an exploration into this style of programming for me, and I prefer its ergonomics to that of the object-oriented way. So I'll take a look at that next. All right, so this is the game that I'm currently working on. So I actually have the components, the systems, and the world structs held in different files just for simplicity's sake. And the subject matter of this game is a little violent, so I hope you don't mind. But we're going to take a look at how I am actually implementing this ECS into an actual game. And we're going to start with the components. So this is a file where I declare components. And these are components that can be reused across different entities to give them functionality. So we created a type of for entity. It's just a U32 though. And then we have they're structs, but they're not really. Essentially, they're just wrappers for an underlying data type. And so we have our name components and our descriptions, our levels, timers, and then health values and skill values, typical things you would see in a game. And down here we put them into pools. We map them together into these pools, which allows us to attach them to the world struct later, and then also to, when we have our systems, tell the systems what kind of pools we want to look through. Down here is an event bus. This is more about control flow for minimizing branch prediction issues. So I use as little ifs and thens as possible. Almost everything is matched. So let's take a look at the world. So here's all those pools that I just showed you, and here they're actually being stored in a world struct for managing state. And this is where they are implemented, which is how we instantiate the world. And then down here we have a spawn. Just like we spawned that goblin earlier, this is how I spawn a human, and here's how I spawn a weapon. You would do the same thing. Everything is an entity. If you want items are entities, you would spawn them the same way. Things that you may only think of as pure data, like a quest, which is typically a name, a description, and then something you have to do. It's like an objective. That could also be an entity. And then we have our systems. So we pass in events, and then they are matched, this is the control flow. So instead of using if-then statements, we have this queue of events, and it goes through each event and matches it, and then runs the required function depending on what event got passed in. And this allows us to have a lookup table handle all the logic of our game instead of there being any branch prediction. And there is ifs and elses within these, but they're small. And if I wanted to, I could actually improve the branch prediction success of these by saying what's most likely, essentially, by using keywords in Rust. And the final component of a game like this is just that there's the actual world, the script, you could call it, that drives. We take in our architecture and then we script using it. So we create me, and we create a bandit, and we spawn a couple weapons, and then we spawn a couple armors. We attach these weapons and armors to our players. It's something we can do because it's an entity system. We're not like pushing anything into any structs. And then we begin a battle. And just so you can see what I have currently in action, it's not super impressive because, again, I'm just exploring the data structure, but it's a time-based game where actions are happening. There's some randomness involved for who's attacking who and when, did they successfully hit or not. But it's the beginning frameworks of a game that I intend to keep working on. All right. So next what we're going to look at is a couple object-oriented and entity component system examples I made to show the difference in speed. Now, this is the object-oriented approach, and it's going to spawn 100 million goblins that have similar structs to what we have before, and it's going to apply a transform to each of them, and it's going to keep track of the time as it runs. So this is the object-oriented approach running in release mode. As you can see, it took 2.7 seconds to spawn them all, and then 178 milliseconds to apply the transform to all 100 million goblins. Now, this is incredibly slow. In a game, you typically want the entire game to update once every 16 milliseconds at least. It's better if you can get down to like 8 milliseconds, even 4 milliseconds. So this is incredibly slow. So we now have the naive ECS approach, which looks remarkably simpler. This uses a sparse set, which is basically a data structure that combines the benefits of a hash map with that of a vector. So it allows you to iterate over things as if they're a vector, but it also allows you to address things directly as if they were a hash map. And if we run the same example, if we run this exact same example that we had in the object-oriented way, but in the entity component way, again, this is 100 million, we're going to see something interesting here, which is that the spawning, and you can see there's an assertion there at the bottom, but the spawning took a little longer because we're inserting everything into not only vectors but also into hash maps. But the systems themselves only took 30 milliseconds, down from 178 milliseconds. So it's over 5 times faster. And 100 million is obviously ridiculous, but if you were to imagine that there was 100,000, you could see how we could get from something that's outside of our frame budget, basically a game that's too slow, you could use this to pull it into a game that's actually fast enough to run in real time, where you're getting the entire game world updated every 4, 5, 6 milliseconds. So this is just a little proof of that our cache line is a significant bottleneck once we're doing high entity counts and iterating over them. So I hope you enjoyed this look at entity component systems and their effect on the cache line and their comparisons to the object-oriented approach.